1, 2, 3, 4. Online. Yes, I'm online. Okay, good. Hello, everybody. So let's do some word problems. This is from chapter 11.1, but a lot of this stuff gets rehashed in Math 101, Math 100 when you're a little bit stronger at this stuff, and a little bit more in Math 101. Uh, so I'm gonna actually take it easy on these word problems. Um, in a lot of them in the textbook, they want you to build the model yourselves. And in this case, we're only going to be considering ones where I give you the model and ask you to solve it in different situations. But I mean, that's not quite as easy as it sounds. One of the aspects of it is we're gonna use change of base to not just look at models but also interpret them a little bit. So things are gonna get pretty fun around here. So before I go on, exponential models and logarithm models both look really characteristic, especially the type we're going to see in our textbook. Exponential models usually look like this. It's not just some number to the power x. There's usually a constant multiplied out front. Alternatively, these are sometimes written a times e to the r times x, where in both cases there's two constants, that constant and that constant, or this constant and that constant, and they're usually given in different circumstances. And sometimes you have to figure them out yourselves. But there's essentially two unknowns, and just like for instance, you saw linear modeling, where we would give you two pieces of information, and from those two pieces of information, you have to figure out what the slope and intercept are. In exponential models, we also give you two pieces of information. Sometimes it's the doubling time. He goes, oh, the ducks in our pond double every 4 years. And then sometimes it's the constant. Sometimes it's two data points. And then we say, this is an exponential model. Figure out what A and B are, and then use it to solve problems. So it's not as complicated as it sounds. Logarithmic models are kind of similar. The deal here is they often look like this: log b of x plus c, where there's two constants, an additive constant and then the base of the logarithm. And sometimes these are written like this: constant out front, ln of x plus c. And in both cases, they're written in terms of ln and e, and that's for a variety of reasons that come down from calculus. So you need to know what ln is. It's the inverse of e. And you need to know this exponential one. We'll see some examples where it's kind of characteristic, but essentially how this is going to work in terms of my assessments is I will give you an equation. I'll tell you where it comes from, and then I'll ask you to solve it, so manipulate it and figure out solutions. But essentially, what it often comes down, what in general these things come down to is figure out what the value of A is, figure out what the value of R is. Ugh, this is getting overloaded with junk. Essentially what these model word problems come down to is, figure out what A is, figure out what C is, or they'll say it's an exponential, figure out what A is and figure out what R is, and then solve the problem. So like I said, it's not as tricky as it seems. So let's see some model word problems. Like I might give you, I might say the money I have put in the bank is A is equal to $200. And then we'll say the interest, wait, it's not yearly, continuously compounded interest rate is R is equal to 0 to 0.2. I guess that's 20%. So maybe I own a payday loan. And then how much money do I have? Okay, wait, hold on. And then I said I'd give you the model. So the money over time will increase according to the model y is equal to a e to the r x, where x is in years. This model is for continuously compounded interest. It's the one the banks use to figure out how much money is in the bank. You put money in the bank and it increases over time. It increases over time using a model called continuously compounded. And this is actually one of the most common places you as a civilian are going to see the exponential. If you become a scientist, you'll probably see the exponential all sorts of places because it shows up in calculus quite a bit. But even your parents, even if they didn't go to school and aren't scientists and are just regular folks who occasionally go to the bank, might have seen E in this context. It gets used in continuously compounded interest, and that's the formula. So in other words, y is equal to 200 e to the 0.2 times x. And then we can ask questions. Hey, how much money after 4 years? And B, when will I have $1 million? That's $10,000. When will I have $100,000? Okay. So how do I answer these questions? These are the types of questions I'll ask you to do in our assessments and in practice. So how do you do them? Well, essentially, I'm going to use this model, this function, to solve it. And so whenever I give you a question, you have to ask yourself what type of information I'm giving you. I always give you a little bit of information. And what kind of answer are we asking for? Okay? In other words, am I giving you X or am I giving you Y? Am I asking for X or am I asking for Y? In the first question here, I'm giving you a piece of information about time. That's the value of X. 4. And I want to know how much money I have. That's the value of Y, right? Dependent, independent variables. So Y is equal to 200 e. I'd use substitution to evaluate this function, times 4. So this becomes 200 e to the 0.8. And then I take out my calculator and I go e to the power 0.8 times 200. And I go, look, after 4 years, my bank account will have $445 in it. Great. It's gone up quite a bit. When will I have $100,000? Well, what kind of information am I giving you? What kind of information am I asking for? I'm giving you information about Y. And I'm asking you information about X, time. When? That's a time question. When? It's a time question, okay? So here's how to do it. We're actually going to use algebra. You set 1,000, 10,000, 200 e to the 0.2 times x. So what we're going to do is we're going to use logarithms and exponentials in these questions to solve for x. Watch how I do it. We're going to do it in a series of steps. Step 1, I want a single constant is equal to the exponential, an expression like that. Right now it doesn't look like that because there's that constant out front, okay? So the first thing I have to do is divide both sides by 200. 1, 2, 3, 4. 200 is equal to e 0.2 times x. Okay, so 200. That's equal to 500 is equal to e 0.2 times x. Okay. Now, to get x out of this expression, I need to use inverse functions. So I'm going to take the logarithm base e of both sides. That's ln. The expression on the right becomes 0.2 times x. The expression on the left becomes ln 500. Now I divide by 0.2 to figure out the value of x. And look, in 31 years, I'll have $100,000. Okay. Let's try another one of these exponential questions. A number of bunnies in the park follow the model y is equal to 4 times 2 to the power x, where x is in months. Okay? Hey, how many bunnies in 4 months? B, how much time? Well, how about when? When are there 6,000 bunnies? So it's natural to see exponential increases like this, where the number of rabbits increases exponentially. Okay, so how do I do this? Why don't you try this question first? Okay. All right. How many are in 4 months? That is a, I'm giving you the value of x, which is time, and I'm asking you the value of y, which is number of bunnies. So I'm going to figure out that answer by direct application. I'm just going to replace the value of x with 4 and then evaluate it. 4 times 2 to the power 4 on my calculator is 64. Now question B. When are there 6,000 bunnies? In this case, I'm asking you when, and I'm giving you a value of y, number of bunnies. So 6,000 is equal to 4 times 2 to the x. Divide both sides by 4. So that's 1500 is equal to 2 to the x. Okay. Let's talk about what to do next. Because, of course, the easiest thing calculation-wise to do is to just apply log 2 to both sides. Right? In fact, let's talk about what happens if you apply log 2 to both sides. I'm going to split the page in two. Just log 2 to both sides. The value on the left becomes log base 2 of 1500. The value on the right is log base 2 of 2 to the x, which becomes x. And now I have to evaluate this number. And how do I do that? I'm going to use essentially the change of base formula. Oh, a pain in the butt. 1500 divided by ln of 2. So that's equal to 10.5507. Going from this to this is actually kind of an annoying job. There's another method. I don't have to take the log base 2. It is the inverse of 2 to the x. It's definitely inverse of 2 to the x. But watch what happens if I just take ln, just some other base of both sides. Ln of 1500, ln 2 to the x. I use the power rule to bring the x out front. And now I just have two numbers. And if you're savvy, you'll note that this expression is exactly this evaluated using the change of base formula. It's the same for a reason. But doing it this way is actually, it's a little bit easier to keep track of all of the different terms. You get the same number. Okay. Okay. How about one more exponential and then we'll move on to logarithms. Um, I have 200, 20 million cesium atoms. The half-life of cesium atoms is, I don't know what it is, so I'm going to make it up. 60 days. So the model for describing the growth, decay, radioactive decay. Or how does radioactive decay work? You have a bunch of atoms in your object, and then randomly some of them they radioactively decay into other elements, and then you have fewer cesium atoms after that happens. Okay, but the model that this follows, you're going to see this in calculus. The model it follows is 2 million times 1/2 t over 60. So every time t increases by 1, you multiply everything by 1/2. It goes down by 2 each time. We saw an explanation of halving things when we were doing another exponential. So that's equal to y. And so, when will I only have one atom left? All right, that's a when question. How do I answer it? That's a y is equal to 1. I'm given that. I want to know what t is. All right, this one's extra weird. So what I'm going to do is essentially what I've done before. Divide everything by 2 million. So that's equal to 1/2 t over 60. Okay. Now I'm going to take the ln of both sides. The reason I take the ln of both sides is because I don't really want to take the ln of 1/2. I don't really want to deal with log base 1/2. So I just want to show you what you get. You don't get anything you need to be afraid of. You just get a bunch of numbers. This is a number, this is a number, this is a number. I can calculate each of those numbers on my calculator. Ln of 1 over 2 million is equal to minus 14.508. 60 is the number 60. And ln of 1/2 is minus 0.69314. And now just solve for t. Multiply everything by 60. Divide everything by minus 0.69314. And that gives you what the value of t. T is equal to 1255 days. So, like I said, I'm going to be giving you these different weird equations, but I just want you to note something in this one and the previous one. The models, instead of describing them in terms of some rando, like this expression gives everything in terms of base e. This model was talking about doubling. It doubled every month, and so the base of it was 2. Half-lifing is about things decaying, how long it takes for half the number to be left over. And so the base over here was 1/2. These things can make kind of a sense to them, and so it's really helpful to be able to interpret that. So, let's do a logarithm question. I mentioned you see logarithms in a bunch of different cool places. Let's do this one. It's the scale of an earthquake. I'm gonna mix up some of the terms just to keep us lively, but the Tippett scale for measuring earthquakes is y is equal to log base 10 of x plus 3, where x is the power of the earthquake and y is the measurement on the scale. Okay. This is like the Richter scale, but better because I made up the numbers. Okay. What rating is an earthquake with power 2? B. How much power for an earthquake to measure 4? How do we do these problems with logarithms? It's not that tricky. We do essentially something very similar to what we were doing before. The first thing in a word problem you have to recognize is what type of information are you giving? Are you given? What kind of information are they asking for? So in the first one, they're giving you the power, which is x, and they're asking you for the rating, which is y. You figure this out just by substituting in the value of x. And then you take your calculator out and you calculate it. So that's log base 10, 2 plus 3. So this is going to be 3.30102. Wow, that means something. How much power does it take for an earthquake to measure 4? So in that case, we're asking about power, and we're given that y is equal to 4. The question here is, what do I do next? Wait, we don't know what the value of x is. And also, this question's stupid. Instead of this one, let's do 9. Okay, so how do I solve this? First off, just like with exponentials, what you want is some number on one side and then a logarithm on the other side, a bare logarithm, okay? So I'm going to subtract 3 from both sides. So that gives you 6 is equal to log base 10 of x. And now I'm going to invert it. I'm going to put both terms on top of 10, that number. If you think about it, this is just supposed to be a number. This is just supposed to be a number. So if I put 10 to that power, it's going to give you the same value as 10 to this power. That's the overall idea. Why am I choosing 10? It's because 10 is the base of the logarithm. The point to all this is that I want to invert the log. 10 to the 6 is equal to 10 to the log 10x, which just becomes x. And so x has to be 1,000,000. You dig it? Okay, so let's try another one. My level at Pokemon is y. The experience I have earned is x, where y is equal to 2 log base 3 x minus 4. All right, so this particular expression isn't particularly useful, but the idea here is, hey, in some video games, your level increases logarithmically with the amount of experience. And that means to get the first amount of experience takes 3, and to get the second amount of experience takes 9, and to get the third level of experience takes 27, and the fourth level experience takes 81. It increases logarithmically, and this means that you level up really fast when you're low level, and it takes longer and longer and longer to achieve the next level. So reaching a really high level is a really high status thing. Okay. So let's cut to the chase here. How much experience for me to be level 8? I'm giving you information about y, and I'm asking you information about x. Plug it into the equation. So again, the point here is that I want to rearrange it so the logarithm is alone on one side. Add 4 to both sides. Divide both sides by 2. Okay. Now, you're going to recognize the base of the logarithm, and you're going to put both of these numbers on top of 3. 3 to the 6 is equal to 3 log base 3 of x, which is x, and 3 to the 6 is 729. Yeah? Alright, so that's how to do those. I expect you to be able to do them. It's just operational how to use logarithms and exponentials. But to be able to solve a lot of these problems, you need to be able to know how to use go back and forth between using exponentials and logarithms. There's one last topic that I want you to know how to do. I'm not sure if it's in the textbook, but it's actually a real cool application. So, here's what we'll call it. We'll call it doubling time. How much time does it take for the thing to double? How much does x have to change for it to double? So for instance, y is equal to 20 times e to the 4x. How much does x need to increase by for y to double? The chief feature about exponential graphs, regardless of the base, is that they always take the same amount of space to double, or triple, or quadruple. If you increase x by a set interval, the value of y will always increase by the same multiple, no matter where you are on the curve. So how do we figure that out? Dig it. What we're going to do is we're going to say, okay, so there's some initial value of x and some initial value of y. Y initial is equal to 20 e to the 4x initial. There's going to be some final value of x and some final value of y. It's final. Okay? We want to figure out how much time it takes for yf to be twice the initial value. In other words, yf divided by yi is equal to 2. We want to figure out how much time it takes for the output to double. Does that make sense? Watch how easy using algebra in exponentials is to answer this question. So what you do is you just plug in these equations into this expression. 2 is equal to y final divided by y initial. That's equal to 20 times e to the 4xi over 20 times e to the 4xf. Wait, I switched those around. The top one's supposed to be f and the bottom one's supposed to be I. The 20s cancel out, and this becomes e to the 4 x final minus 4 x initial. So 2 is equal to e to the 4 x final minus x initial, which is the change in x. And now I just solve this equation for delta x. Take the log of both sides. So delta x is equal to ln of 2 over 4. So every time x increases by 0.1732, the value of y doubles. Isn't that fun? Let's try another one. All right, so I set yf to equal 70 times 3 to the x final. I say my initial value of x, 3x initial. I want it to double, so y final divided by y initial needs to be 2. So that's 70 times 3x final over 70 times 3x initial, which equals to 3x final minus x initial, and that's my delta x. And before you go on, you should be saying, hey, why is it double? Shouldn't it be tripling? I don't know. I said that all exponentials double over regular intervals. Sometimes they half over regular intervals. It depends whether you're going forward or backwards. But multiples of 2, right? Take the ln of both sides. So this becomes delta x times ln of 3, ln of 2. So delta x is equal to ln of 2 over ln 3, which is equal to 0.6309. When x increases by this amount, y will double. Isn't that fun? Okay, so there's an alternative way of doing this. Dig it. Tell me this. What's the doubling time of that? How much does x need to increase for y to double? The doubling time of this one is 1. Every time x goes up by 1, the value of y doubles. Good. How about this one? 2 to the x over 3. How much time does it take for y to double? Well, every time the input x increases from point to point but 3, it's going to double, right? Whatever this number in the denominator of my exponent is, that's the doubling time if the base is equal to 2, right? And you can even do this backwards, right? So it's like 2 to the 4x. What do you think the doubling time of that is? You can write that as 1 over 4, so that's 2 to the x over 0.25. And so the doubling time is equal to 0.25. Doing it this particular way, just interpreting this denominator, it's a little bit annoying, so don't do it that way. Instead, here's how you do it. What you do is you go, okay, You take your expression and you ask, what's it going to take for that to be equal to 1? Okay. So long and short of it is, if the base here is equal to 2, you're on easy street for calculating doubling time. And the super nice thing about this is that it's really easy to make the base of something 2, right? So for instance, let's consider this last problem. Y is equal to 30 times 3, is there a thing on top? 3 to the x. I can use the change of base formula to change the base of the exponential. So you can put 3 in parentheses there. So this is 2 log base 2 of 3 times x. So the exponential becomes 2 log base 2 of 3 times x. And then you can use this particular number to figure out what the doubling time is. So the doubling time is going to be when log base 2 of 3 delta x is equal to 1. So delta x is equal to 1 over log base 2 of 3 is equal to log base. All right, hold on. This is ln of 3 divided by ln of 2. 1 divided by answer, 0.6309. Oh, same number. Yeah. So you can use change of base. The base as either 2 or 1/2, and then interpret doubling time. If that didn't make sense to you, I don't think it's that important. This is just a fun thing to do with exponentials. Okay, that's it for this particular thing. If you've watched this and you've done the worksheets, you can now challenge the second to last assessment. After this, it's trigonometry.